All right, ladies and gentlemen, recording is started. First, too bright. We need to turn some lights down, or are we okay here? We're good. Nick's good. Anybody else? All right. On Friday, we started talking about what a star was, and we talked about the idea that this section, this unit, really starts us off in the smallest thing we know about, the nucleus of an atom, and then it takes us through up to some of the biggest things we know about, and that being stars. So, right, first, a star, a hot collection, or a huge collection of plasma and very hot gases. Right, it's plasma because sometimes it's not really part of an atom. Right, it's pieces parts, and that in the process of that star in its lifetime, it takes those pieces parts and forces them together to become actual atoms, or at least the nucleus of atoms. And then stars emit energy by fusion, and during fusion, right, E equals mc squared, some of that mass converted into energy, but because there's so much mass there in the star, lots of energy is released, and that's what a star is. So we start talking about how to classify stars and how to put it together and distinguish one from the other. First thing we talk about is how far, and that gets us into the light year, right? Don't be confused, right? Despite its name, light year is not a time, it's a distance, right? It's the distance that light travels in a year. Considering that it goes 186,000 miles every second, how far light travels in a year is pretty far, right? Here, 9.5 trillion kilometers. So it's, that's one light year. And the closest star to us, other than the sun, is 4.3 light years away. That's the closest star. So when we start talking about these distances, it's mind-boggling how many zeros we're talking about at the end. The other thing we talk about when we're identifying the location of the star was parallax. The idea that depending on where we look at something, its position or apparent position can change. And we did the example. You did? I want to make sure you're okay. That its apparent position can change, right? That we did the example with the thumb, and if you close one eye and close the other, open that and close the other one, your thumb appears to move based on where you're looking at it from. And because of that, we can figure out how far a star away is. When these two lines intersect, we know the distance in our orbit from one side of the sun to the other, so we know one side of a triangle, we can figure out the other sides. Good there. All right. Then we started getting into how do we classify stars? What are the characteristics? So first thing we talked about was color and how that relates to temperature. Blue, white stars are your hottest stars, yellow are your medium stars, reds are your coldest stars. That's all relatively speaking, right? They're all really, really hot, but relative to each other, some are hotter than others. Some give off more energy than others. Then we talked about apparent brightness versus absolute brightness. How much energy do we view of that star versus how much energy is it actually giving off? And that depends not only on how big that star is and how much energy it gives off, but also on how close it is, right, and where that object is. And that's about where we got to at the end, right? And we talked about these lights, apparent brightness versus absolute brightness, that this one that's closer appears brighter to us, not necessarily because it's giving off more energy, but because it's just closer to us, right? That all of them really are the same, or at least close to it, but this one's closer, so it looks brighter. Good there. Okay. All right. The next thing we want to know about stars is what they're made out of. Did we do size and mass? Did we figure that? Yeah. Gravitational effects give us the mass of that star. All right, composition. What is it made out of? Well, the only thing that we have to go on in order to identify anything about a star is what we see about it. We can't go and get a sample of it, so we have to examine, well, what is it doing to the stuff around it, and what energy is it giving off? We look at the light that is emitted from the stars and analyze it using something called a spectrograph. And there are different kinds of spectrographs, and some of them work different ways, but each star gives off a characteristic amount of energy. And you'll do this way more in chemistry. We don't do it so much in here, but this is an example of an absorption spectrum. What we find out is that the spectrograph looks at all the frequencies of visible light that are given off. It's scanning for all of them. And when we look at different stars, what we find out is that we end up with some distinctive patterns of black lines. So we have this continuous spectrum. Not that a star is giving off all of these frequencies. The spectrograph is scanning for all these frequencies, but it only finds certain ones. And when it finds those certain ones, it automatically takes them out of the spectrum and creates a picture, right? So it's looking for frequencies and only picks up certain ones. But what we find out is that these certain frequencies that we pick up are the same kind of frequencies that we observe from materials here on Earth. That each star has a unique pattern that comes from the spectrograph. And this pattern, because it matches the pattern of materials that we have here on Earth, we then make the conclusion, oh, well, if helium here on Earth makes a certain pattern in the spectrograph, and we get that same pattern from a star, we put 2 and 2 together and go, we think the star is made out of helium. Do we know? Not exactly, because we've never been there, but the evidence suggests that that's it. So even though we can't actually get a sample of that star, based on the energy it gives off, and then comparing it to the stuff that we have here on Earth, we can make a pretty reasonable assumption about what kind of things stars are made out of. Most of the stars in our solar, or not in our solar system, most of the stars that we observe here from Earth have a similar composition to the sun. Somewhere in the upper 90% of hydrogen and helium. Now, the ratio of hydrogen to helium is something that we'll talk about in just a second, because that determines how old the star is. But upwards of 96 to 99.9% of a star is made out of hydrogen and helium. Very similar to our sun. And like I said, the ratio of hydrogen to helium, though, that's different for different stars because that depends on how old they are and how long they've been around and all that stuff. Okay? Good there. All right. So we take this information, where stars are, how hot they are, what they're made out of, et cetera, et cetera, et cetera, and we start putting it together. And we end up with something called the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a graph showing two things, right? So it's got two axes. Surface temperature, which is determined by the color. We said that determines the color of the star. And then the absolute brightness, which we have to sort of figure out, right? Because absolute brightness is not what we see here on Earth. We see apparent brightness. So we have to put a couple of different things together about the composition and what percentage of hydrogen to helium it has, et cetera, to get us the absolute brightness. And it looks, measuring these characteristics allows us to estimate the size of the star, estimate how far away stars are, and predict what will ultimately happen to those stars. Based on our experience with previous stars and what we've seen stars of that size and that composition do in the past. The Hertzsprung-Russell diagram. Most of the time we shorten that to HR, as you could maybe imagine, because Hertzsprung and Russell saying that a lot. You know. All right. Are we ready? Okay. Hopefully you've seen. Have you guys seen this picture before? Something similar to it. If not, here it is. All right. Here's the Hertzsprung-Russell diagram. Okay. Notice, like I said, it's a graph, so it has two axes, right? An x-axis and y-axis, and on those two axes are surface temperature, relating to the color, and the absolute brightness. Now I know I don't understand why on this graph, the x-axis runs from the highest temperatures on the left to the coldest temperatures on the right. Notice, right, 50,000 kelvins here on the left, 30,000 kelvins here on the right. Last time I checked, that's not the way we counted. But like every HR diagram that I've seen in the book always runs this way. I don't know why they decided to do it. Okay. So, two things, right? Surface temperature, absolute brightness. What we find out is that where stars fall on this diagram tells us about how big they are, how old they are, and what will ultimately happen. And that's the three things that we wrote down before. So, the first part we want to look at is, these are some pretty sweet graphics here. I'm going to tell you this right. The first part we want to look at here, so, absolute brightness on the y-axis. If we look, right, you can see there on the side, it says increasing from the bottom up. So absolute brightness. Our brightest stars are up on the top, faintest stars are towards the bottom. Now remember, that's not necessarily how they look here on Earth. We're talking about the absolute brightness, which relates to their size. Okay, so your brighter stars are farther towards the top, your fainter stars are towards the bottom. And then on the x-axis, right, temperature. Hot stars are on the left, cool stars are on the right. Again, don't ask me why they did it that way. It's how it shows up. Mine has color, and you can see that the bluer ones are on the left and the red ones are on the right. You guys don't have the color, obviously, but it does actually say there at the bottom, right? Blue, blue, white, yellow, orange, red, red. Okay. All right, good there. Most of the stars that we find out there in the universe fall along something that we call the main sequence. The main sequence is a diagonal band that goes from the bottom right of the graph to the top left of the graph. And if you look at your picture, it's labeled as such. So, bottom right, top left. There it is. Okay? There's our main sequence. What we will find out here when we start talking about the life cycle of a star is that these are stars that are in their prime, right? They're doing their thing, they're doing their star stuff, and we'll talk about what that is here in just a second, right? But that's where the majority of our stars fall. Later on, we'll talk about how long they stay on the main sequence, where they show up on the main sequence, because you'll see, right, there's a big variety of stars on the main sequence. Blue hot ones, red cold ones, right? They run the spectrum. Where does a star show up? Does it move up or down the main sequence? We'll talk about that in a little while. Okay? All right. Supergiants and giants. Again, on your sheet, right, you can see top right of the HR diagram. Not very hot, but very bright. That's why they're towards the top, because they're very bright. But you'll see from the picture, right, where they're labeled supergiants and giants, they're more towards the top right. And we said that things towards the right aren't very hot. So if they're not very hot, but they are very bright, that leads us to the conclusion that they have to be big. Have something that doesn't give off a whole lot of light to begin with, but it's really, really big, it can appear bright. For example, right, if you have one, let's say, let's say 100-watt light bulb, right, you can fill up a room with candles and make it just as bright as one 100-watt light bulb. But how many candles are you going to need? A lot, right? So these stars, they don't give off a whole lot of light, but because they're so big, they appear very, very bright. Okay? We're talking about stars that are in the range of either 100 to 1,000 times the diameter of our sun. And I think I kind of mentioned to you guys on Friday, our sun, sickeningly average when it comes to stars. It's like seriously right down the middle of the spectrum of stars. It's like medium hot, medium big, medium bright, obviously not to us, but in the big picture, right? So when we talk about different kinds of stars, we obviously compare it to our sun for two reasons. One, it's pretty important to us, right? But two, it's very, very average. Okay? So your giants and your supergiants show up here in that top right. Okay? Some of these stars, if you look at stars, you may know some of these names like Betelgeuse, and Aldebaran, Pollux, Polaris. It's kind of an important one. These are pretty famous stars that are in pretty famous constellations. We won't go into that a whole lot now, but if you know anything about them, they are. All right, good there? Okay. Next, you got your dwarfs. Not offensive, right? Just what we call them. Right? We're sensitive to their needs. So, bottom left-hand corner of the HR diagram. And because they're in the opposite corner from the giants and the supergiants, all of their characteristics are pretty much opposite of the giants and the supergiants. They're very hot, but not very bright. I guess if we want to talk about a practical example of this, it would be like a sparkler, right, over the 4th of July, right? The sparkler is super, super hot, but it doesn't light up the room very much, right, because it's pretty small. And that's the case with these as well. They have to be small in order to give off, for the amount of energy that they give off, right, how hot they are, but because they're not very big, they just don't light up very much. Sorry, did we get that? Yes. So, your dwarfs, right, down here in the bottom, right, not too many that we know about there, right, not very many named, because we don't see too many of them here, right? They're not very bright, so they don't show up very much here on Earth. All right, it's good there. Okay, is that the end of that outline? Okay, so now let's transition and let's talk about, okay, what determines where these stars end up, either on the main sequence, why do they end up here, why do they end up here, right? What determines that? And that then leads us into the life cycle of a star. It's kind of like a baby book, but for a star. So, how does it start? How is it ultimately going to end up? Here we go. Scientists look at different types of stars, and they study the energy that they give off and the composition to find indicators of how they age. Okay, so we talked about that before, right? Now, looking at stars, we can figure out what they're made out of, what their composition are, and especially the one thing that's very important is what's the ratio of hydrogen to helium? And we'll see why that is in just a second, right? Because if we can talk about if there's more hydrogen than helium, if there's more helium than hydrogen, that tells us something about how old that star is. So, we start off as a nebula. And a nebula is just a big cloud of gases and dust spread out over a really big region of space. Where does it come from? Generally, it comes from an old star. And sometimes it could be left over from the Big Bang Theory, whatever it might be, okay? But anything that's in our universe right now started at the Big Bang Theory. We just keep recycling it over and over and over again. So, big cloud of gases and dust, right? Maybe a little plasma, some pieces, parts, just a bunch of collection of stuff. But that collection of stuff has mass. And if it has mass, it has gravity. And if it has gravity, it starts pulling itself together. And I said the answer to questions now for the next 2 days is gravity. So gravity starts pulling that dust and gas together in a denser cloud. And as we get more stuff closer together, more gravity. And as we get more gravity, we pull more stuff in. And as we pull more stuff in, we get more gravity. And as we get more gravity, we pull more stuff in. It just keeps accumulating bigger and bigger and bigger and bigger. And because we start squeezing things together, and as gravity is pulling them in, they go faster. And as they go faster, that temperature begins to rise. And there's eventually so much gravity, so much pressure, and so much temperature that it starts fusing these dust and gas particles together. And we get nuclear fusion. Remember the gist of nuclear fusion, right? If you had to explain nuclear fusion in one sentence, what is it? I kind of did this last week, right? But if you had to explain nuclear fusion in one sentence, what happens? Any good?
Putting things together.
Putting what size things together?
Atoms.
Well, how big of atoms?
Small atoms.
Small atoms together to make
Bigger atoms.
atoms, right? So we're starting off small, we're starting to put those atoms together, right? And that's what fusion is. So then, we hit a critical point. If there is enough mass, something that we refer to as a protostar. So how much mass this nebula of gases and dust has will determine what happens next and if it makes the cut. Okay? Gravity is pulling everything together. As fusion starts, it starts releasing energy. And as things release energy, they get hot. They make the things around it hot. And when things are hot, what do they generally do? So we know that the particles move faster, right? But generally, what happens to the volume of things that are hot?
Increases.
It increases, right? So now you've got gravity trying to pull all this stuff together, but the energy from fusion making it hot and trying to push stuff outward. If those two forces, the inward pull of gravity and the outward push that is coming from the energy being released from fusion, if those two things balance up, we get ourselves a star. And we call that, protostar. So, right, here is big nebula, right? Gravity's pulling it together, makes it into a protostar. Fusion starts. If we get a nice balance between the outward push from the energy of fusion and the inward pull of gravity, we get ourselves a main sequence star. If there's something about that, if there's something about, oh, by the way, you have most of these pictures, I think, on the next page. You have this one? Yeah, this one isn't real exciting. But if you want to draw it, you can. But the rest of the pictures will show up there. So, if you don't have enough mass, or if that balance between gravity's inward pull and fusion's outward push, if it doesn't balance out right, you get something like Jupiter. Okay? Jupiter is a big collection of gas, just like the sun is. But there wasn't enough mass there to get that balance just right between fusion, right, or maybe you didn't even start fusion, right, or there was too much fusion for the amount of mass that was there, it just kind of blew it apart, or gravity was so strong that it just squished everything together, but not to the point that it started fusion, right, there wasn't enough gravity there, right, a big collection of gas and dust, but it's not quite there, right, and that's pretty much what, we find that out there, but, like I said, we don't find it a lot because we don't see it. Jupiter doesn't give off its own light. Okay? So that's what could happen. And you figure that happened somewhere in the universe, that you have these big collections of dust and gas, like Jupiter, that just didn't quite get there. Right? Didn't quite have enough to, didn't quite have the juice to make it onto the big stage. Right? And that big stage being, right, our HR diagram. Okay? That's our big stage. That's like, Broadway or Hollywood or whatever you want to think about it, right? So, the one really important factor that determines where these stars end up on the marquee, right? Now I'm going with my Broadway. I'm going with my Broadway analogy here, right? So the HR diagram, that's your Broadway right there. So, right? What determines where they end up on this HR diagram is mass. That determines where they end up. So, there's your HR diagram again, okay? Main sequence. These are like, your movie stars, right? These are your like, you know, B-list stars, C-list stars down here, and this is like George Clooney up here. Right? There he is, man. He's, you know, right? Johnny Depp, right? So anyway, but that's your main sequence stars. Over here, right? These are your old guys who like show up and get like $1 million just for being in a movie because that's like De Niro, you know? He's
Nicolas
like,
Cage.
What?
Nicolas Cage.
Nick Cage is down here, all right? He's like, this is him, man. Nick Cage has kind of worn out his welcome. He's down here in the dwarf section, right? Yeah, this is like De Niro, you know, like Marlon Brando, kind of, you know, that kind of these old guys that just are like super huge, just kind of show up and like they put their name on the film and they're like, man, wow, he's in it. I gotta go see it now, you know. All right, so that's kind of, and then yeah, Nick Cage, he's down here. So all right, so just. Yeah, he's kind of crazy. He's kind of bright, but he's so small that nobody notices him anymore. So yeah. All right, where they end up on here depends on the amount of mass they have. Okay, so big, huge stars, right? Literal stars, not George Clooney. Okay? Big, huge stars, big, huge nebulas, lots of mass, come together and form very bright and very hot stars. Okay, these are the questions that show up next to the HR diagram that you don't necessarily have fill in. So the first question that shows up there, just make sure what it says. Where are stars with large masses located on the HR diagram? Large mass stars are located in the top left of your main sequence. Okay? So, if they're to the far left, how hot are they? They're very hot. Okay? If they're in the top, right? The fact that they're on the left means they're hot. The fact that they're on the top means what?
They're bright.
They're bright. So they're very hot, very bright. Okay? Generally, they're in the blue, maybe in the bluish white. But there's a trade-off. The only way that a star ends up very hot and very bright is if it gives off a lot of energy. If it gives off a lot of energy, what does that mean it's doing a lot of?
Fusion.
Fusion. That's how a star gives off energy. If you do a lot of fusion, that means you run through your gas really, really fast. Okay? So these stars that are up here on the main sequence, these really, really bright stars, right? They're really, really bright, but they last the shortest. Again, relatively speaking, we're still talking about hundreds of thousands of years, but in the case of a star, that's not very long. All right? So those stars up on the top left, big, bright, hot, but don't last very long at all. Good there? All right, got that? So next, again, these are all mass. So these are your biggest stars. And as you can see from the picture, right, the dots up here are a bigger size because they have a lot of mass. So now let's go. Look where our sun is, right? Like I told you, yeah, right? There it is. Just there, C. It's like 75%, right? It's just right there, okay? So let's talk about our sun next, okay? So stars with masses that are similar to our sun. Not as bright, not as hot. Why? Because they don't have as much what? You said what really determines where they start, where they end up on this diagram? Mass, right? Sun just doesn't have as much mass as some of those other stars. So, it's not as bright, not as hot. The trade-off being, though, right? How long is it going to last? It's going to last longer than these stars up on the top. Why? Because it doesn't do as much fusion. If it doesn't do as much fusion, it doesn't run through gas quite as quick. Now, it doesn't have as much gas, which is true because it's not as big, but it doesn't run through it quite as quickly. Right? So, these stars last much longer than your blue stars because they don't do as much fusion. They don't convert as much hydrogen into helium, and that makes them last longer. And then you can probably start filling in the blanks as far as the last part, right? These stars down here on the bottom, okay? Bottom right, small masses, cool stars, relatively speaking, right? We're still talking in the range of 3,000 to 4,000 Kelvin, which is really, really hot, right? But relatively speaking, they're cool. Okay? They don't give off as much energy. They're not as bright. But they last really, really long because they don't use as much hydrogen and turn it into helium. It doesn't, You know who I'm thinking of here as far as this part goes? Right? Anybody see the Princess Bride? Princess Bride? You know the guy who's like the mastermind criminal who like kidnaps the princess. You can see Wolf, that guy. You know, he's still like in movies. He never really has like a big part or anything, but you always know who he is. You know, it's like that's him down here. He just lasts forever, right? He's never gonna make it to the big stage, but he'll be around forever. You know. So, say again. Kevin Bacon, that's a good one. I think Kevin Bacon I would think is somewhere kind of in here, you know, like maybe up towards this part here, you know. I mean, he's not like a super mega star, you know. He's more of a cult figure than anything, you know. But, I mean, if you have a game named after you, right? 7 Steps to Kevin Bacon, whatever. I mean, you know, like you gotta have some cash in, you know. So. But anyway, yeah, like this guy here, that's like the guy from Princess Bride. You know that guy, and he's in all kinds of stuff. But yeah, he's not really like.
Or Nick Cage.
What?
Or Nick Cage. Nick Cage has lasted.
Nick Cage down here, man. I'm dissing Nick Cage today.
He's bad.
Yeah, he's just like. I mean, he used to actually like back in like the '90s. Nick Cage was like Bruce Willis. He was like in these action movies and stuff like that, and they just kind of went crazy. Like he just sort of went weird. And we're like, what's up with Nick? Like nobody wants to hang out with him anymore. Yeah, it's like, what's going on with Nick? Like, why is he all weird? Like, so, I mean, he was cool. He used to be,
there was a hoax online that he like died.
Yeah.
In like a snowboarding accident. I think that was just so that people like to see if people would care.
Yeah, and most people were kind of like, all right.
Whatever, man.
So yeah, like.
I don't even know who that is.
So. What?
Weird like Johnny Depp, but everyone still loves him.
Yeah, Johnny Depp. He's like Johnny Depp's still. Yeah, he went weird like Johnny Depp, but everyone was like, oh, it's so cool when Johnny does it, you know, like. So when Nick does it, it's like, what's up with Nick? So. Anyway, so that's where we go. And when stars form, when they have that balance of fusion and gravity, they end up on the main sequence. Depending on how much mass they have, that determines where they end up on the main sequence. So that's good. And stars stay there, you know, as long as they have that balance of fusion pushing outward and gravity pulling inward. Once we get to the end of that balance, and that balance is determined by the ratio of hydrogen to helium. Once we start getting to the end of that ratio, that's when interesting things start happening. So, let's talk about what happens next. So we got this big nebula, gravity pulls it together, we start fusion, gravities pull, fusions push, we end up with this nice main sequence star. What happens next is really determined, again, by how much mass this star has. So, stars remain stable as long as the outward push by the energy of fusion balances the inward pull of gravity. Okay? We've got to have that balance to have a star remain stable. that's going to remain stable as long as a star has hydrogen and it converts it into helium, because that's what happens in fusion, right? Remember, we take small pieces, put them together to make big pieces. Hydrogen and hydrogen isotopes get fused into helium atoms, right, or helium nuclei. As long as that's happening, we're all good. But once that doesn't happen anymore, and it doesn't happen generally because fusion slows down. We talked about that fusion is a hard thing to do. Why is fusion a hard thing to do? Any good?
We can't get anything hot enough.
Because why? Why does it have to be hot?
Can't remember.
Help? Why does it have to be hot? Nick, good.
Because it has to be a blend.
Why? Why does it have to be hot for us to do fusion? That's help. Help. Why does it have to be hot to do fusion? What are we trying to do in fusion? Take small whats and make them into big whats? Atoms, but specifically what part of the atom? Nucleus. What were you going to say? Oh, you're going to say nucleus. So we're taking small nuclei and making a bigger nucleus. There's.
So we can bring the protons together.
Do those protons in the two small nuclei like being together? No, right? Because they repel each other. So it has to be hot enough to squeeze them together. When you're talking about hydrogen, you're talking about squeezing one proton together with another proton. Sometimes there's neutrons involved, but they don't repel each other, right? One proton, two protons. But now, if you're talking about squeezing helium together, what do you have to do? How many protons does helium have? 2. So now if you're going to squeeze 2 heliums together, right, you got to get 2 protons and squeeze them into 4. Harder or easier than squeezing 1 and 1 into 2? Harder. The more and more helium a star has, the harder and harder it is to do fusion, because it's more protons, more repulsion. It's harder to do. All right? So, as long as we get this inward pull from gravity and outward push from fusion balanced, we're good. When we mess up that balance, that's when we mess up the star. And we will pick it up from there tomorrow. If you take a look at the calendar, a couple pages from your book that relate to this stuff, I think these pictures actually that you see here will show up in that book as well. So you can check those out if you want a preview for tomorrow. There's also some questions related to the life cycle of a star too.